where he is currently serving as TUM ambassador. Prior to this, he served for 23 years in all academic ranks at the faculty of Cornell University. He received his PhD in theoretical and applied mechanics from Cornell, after which he started his academic career at the University of Minnesota, where he is currently. Professor Zabaras' current research focuses on integration of computational mathematics and statistics with machine learning for data-driven modeling and design of complex physical systems. Today, Professor Zabaras will tell us about his research on physics-informed learning for multiscale dynamical systems. And Professor Zabaras, we're glad to have you with us. With this, I'll hand it over to you.
Thank you for the introduction. I was just looking at the long list of participants in the seminar, and I see lots of friends from around the world. So I noticed lots of old friends from Rio de Janeiro are there. Surprised, so glad to see them virtually and everybody else. So what I'm going to do is I'm going to try to give you a very sort of high-level overview of recent work on modeling with deep learning multi-scale dynamical systems. And I will not go in depth in any of the topics, but hopefully I will give you enough information to see both the complexity and the challenges that this area needs to address in the days ahead. So physics informed can mean a lot of different things, and I am not going to even try to define it because it's a very murky area in the literature and politically actually very complicated. So I use the word physics informed to define using AI for problems where there are physical constraints that somehow we need to be aware and possibly enforce them. So let me give you a high-level introduction on the type of things at least you will see on the first part of my presentation. So we work with problems governed by differential equations. So you can think of X being some high-dimensional property and Y being some multi-output, which is also high-dimensional. So this can be, let's say, a permeability field. This can be a velocity or pressure field. Can be anything you want to, but X is the input and Y is the output. And we, generally speaking, we're interested not just to solve with neural networks the underlying PDEs, but we also like to build surrogate models that they're much more efficient than other traditional techniques ourselves and many others have used the last 10, 20 years. So what I'm going to do is I'm going to try to emphasize, at least in the first part of my talk, building the surrogate models from X to Y using zero data. And for those who have not heard me speaking on this, so let me try on this introductory slide to tell you what that more or less means, right? So we have the governing equations from X to Y. If you're a finite element person, think of solving this as a variational problem, that somehow there is a potential V that upon minimization will actually give you the underlying solution Y for a given X. Now, what I'm going to do is I'm going to turn that problem a little bit upside down and pose this mapping from X to Y as a problem of sampling from a Boltzmann-Gibbs distribution of the form e to the minus beta times the potential, with the idea being if you start sampling for a given X from that distribution, you will actually sample in the mode of the distribution, which will give you the minimizer of the potential, which is what you need. All right, that would be the solution to the problem. So now, if you try to actually sample directly from this target distribution, that's an even more complex problem than solving the original PDEs. So what we will try to do is we will try to build variational approximations of this target distribution. And that's where AI techniques come. And the concept of no data implies that the only thing that I would need is I would need to know the potential and have the means to evaluate the potential for different realizations of X and Y. And actually, you will see that to be more precise, you don't really need the potential, but the gradient of the potential, which is the force field. So you need to be able to evaluate the force field for X and Y, that they are samples from approximate distributions, because again, we cannot sample X and Y from the exact distribution. So this is what we will try to do today, and at least in the first part of my talk. And the idea of mapping from X to Y and sampling from some variation or approximation of this distribution will follow what I call an encoding-decoding approach. So the input will be encoded to some latent variables Z, and from there we will decode back to Y. Here I have Zx and Zy, but let's try to be simple to start with. Okay, so let me start with some trivial example. So if this was Darcy flows in, driven by some, let's say, random permeability K. So the problem is to build a map that will allow us from every K to compute what the pressure U is and what the fluxes tau will be, okay? And you can think of this problem as a minimization of some potential, which can be a mixed Lagrangian written in terms of tau and U. And the actual problem here is actually a minimax problem, but that doesn't add much complexity to the problem. And if you don't have this Lagrangian, you can think of posing this potential in terms of residuals in the PDE and the constitutive equations. And of course, you can take a weighted average of all of these things, but somehow we're going to assume that we have some potential that somehow, when you optimize it, it gives you the actual solution of the underlying PDEs. All right. We are going to, throughout the whole presentation today, we're going to use convolutional neural networks. So we're going to treat both the input field X, like the permeability that I had before, but also the responses like velocity, pressures, and whatever else you have. We will treat them as images, either in 2D or 3D. And so when I say I'm going to predict a solution, I mean really I'm going to predict a solution everywhere as a pixelized representation. So for example, the input X will be the permeability at each pixel S1 to S and S. And for now, I'm assuming that I have a regular, pixelized representation of these images. So what I am not going to have time to discuss the merits of doing convolutional neural nets for these AI approaches to surrogate modeling versus fully connected models. But let me emphasize the following important aspect. We are really looking to build for a given X the solution Y as a mapping from some latent space Z to Y. And literally, even though Z can be the encoding of some input, the input X, I want you to think of Z for now being arbitrary. So for a given X, literally, we say, let's say you take some Gaussian Z and you build a map from that Gaussian Z to the output Y, and you represent that mapping as a complex neural network. So the mapping that I will be looking at is a mapping from some latent representation to the response of the system Y. And when you see gradients, every operation that I need to be able to compute the force field will be operations on images. So gradients will be computed with Sobol filters, and you will see the type of calculations you get. They do have nice multi-scale form that you don't see much in the fully connected network representations. So this slide doesn't mean anything beyond the fact that when you need to evaluate for a given X, the potential or the gradient of the potential, all the operations can be written down as pixel-wise operations on images. And that's what this slide more or less says. Okay, a little bit about this probabilistic approach that we use and how it is possible to actually lead to the ability to do surrogate modeling with zero data. So remember, the exact distribution from which I want to sample is this Gibbs-Boltzmann distribution, where E is my potential, okay? The normalization factor is not known in general. And this is a very high dimensional distribution, so you cannot sample directly. So what we will do is we will build an approximate variational distribution that I denote here P of theta of y given x. So this is a conditional distribution of y given x. And what I have here is I am computing this approximate variational distribution of y given x by minimizing the distance between the joint variational approximation for the joint of x and y and the exact distribution of x and y. And I call this the reverse KL divergence because in practice, in variational methods in machine learning, what you do is you minimize the distance between the exact distribution and the variational distribution. So here I take the variational and its distance from the exact distribution. Now, why is that? Because when you substitute this Kullback-Leibler divergence distance and you after just maybe one step, you come up in the equation on the bottom and you can immediately recognize that it has two terms. One term involves the energy and it has an expectation with respect to this variational approximation. So effectively, what you will need to do is if you try to minimize this, you will need to be able to calculate the gradient of E, which is the force field, at samples, but these samples, they're not samples from the exact distribution, but from an approximate distribution. So as you build this approximation and you try to improve it through the parameterization theta, it will be easy to sample from that approximate distribution, and then it will be easy to evaluate this potential or its gradient. And of course, there is an expectation on x because x is random as well, but that adds no further difficulty. So again, we don't need any data because this expectation here is with respect not to the exact conditional, but to the approximate variational conditional distribution. So the first term minimizes the energy, so you can affiliate this with optimization methods, variational methods, let's say in finite elements, Galerkin methods, and the like. But then there is another term that maximizes the entropy, and it tells you that for a given x, the samples y that you get need to be as diverse as possible. And just to make it interesting, even if your problem is deterministic, obviously this leads to a generative approach that gives you a distribution of y given an x, right? So even though the problem is deterministic, still you need to be able to generate a variety of y. If this term basically collapses to a single mode, you will see that you will not alone be able to minimize the energy and solve this type of problems. You will see lots of diagrams like this, but I don't want to elaborate a lot on this slide, but let me just say that the approaches we use, at least in the first part of my talk, are based on flow models. So they're invertible neural networks. And what is interesting about the approach, we try to mimic the multi-scale nature of the problems of interest. So in going from X to Y, we are actually extracting coarse-grained features of the input X that I call here Xi. And this coarse input features Xi condition the corresponding output at that scale. And Z are latent variables that you will need to sample. So in training, you're going to go from, you're going to start with some X's. The loss function is going to define in terms of the potential. So you're going to move this way up. In testing, you will simply sample these Z's and condition on X's for a given input X, you will compute what the Y is. But the message here is that somehow this architecture tried to explore the multi-scale nature of the problems of interest, and literally we're solving in a stochastic way multi-scale problems, and in each scale the input is represented with these coarse features that I call here Xi. And by the way, this whole thing is called, of course, an invertible neural network because the same all operations on what you see can be from bottom to top and also from top to the bottom, and the whole network is invertible. So these methods work, and you can see here predictions for a given test input X for the Darcy flow problem. On the top, you can see the finite element solution, and this is the mean pressure and horizontal and vertical fluxes, and the rest are the statistics that result from the generative model. Okay, this techniques, you can see on the bottom it says KLE 100, KLE 256. There is no KLE or anything like that. I just wanted to generate input data of different complexity. So that's what these numbers imply. And these methods have been pushed up to dimensionality 5,000 with very fine discretization. So this pixelized image can be very fine, very well represented, which is, generally speaking, with convolutional neural nets, is a challenging problem. Okay, so let me keep moving and discuss a little bit about how we extend these problems to a dynamical setting to start with. So, what we have now is, we have a dynamical problem, and for a given input X, we are going to learn a whole time series that I call here U. So UN plus 1 is the solution at time n plus 1. And what we're going to do is we're going to develop, again, a deep learning technique that uses no data. And so what is the idea is to build a map from the states of the system at a few previous time steps to the current time step. So you can imagine a similar strategy to what I had before, where I had the input and then I had an encoding, decoding states. So now I have the output for a given input. So the output at a few time steps that I encode to these Z variables, and then I decode to the response of the system at time n plus 1. So in practical sense, what we are trying to do is we say, if you have seen the state at a few time steps, can you predict what the next state is? So the system is trained by trying to minimize a discretized version of the potential, okay, by somehow learning this mapping from these states at these k previous steps to the next step. And the idea, of course, is whatever you saw with the previous invertible neural network architecture, you're now going to have to unroll it in time with recurrent connections. And that's what you see in the picture here. So what the system, the way it is trained, it starts actually trying to learn what the solution is in terms of some parameterization of the network. And then it tries to match this solution that comes from this network prediction to the solution of a time integrator that itself involves the parameterized unknown solution. So we are trying to make the solution that the network gives to be consistent with the governing discretized differential equation of this dynamical system. So think in a sort of a simplistic manner, if you had data, what you will do is you will say minimize the response of the system from the given training data. That's an L2 norm. I don't have data, but I know what a time integrator will do because somehow I have the solution of the previous steps. And I include here UN plus 1 to allow implicit schemes as well. So I want this to match that in the L2 sense. So there is, not to be confused here, we are not, with finite element calculations and the likes, there is no matrix inversions. There is, we can use implicit time integrations. The only thing we need to be able to do is evaluate this force field that I referred to before for different realizations of this time series. There is a Bayesian version of this whole model, and the Bayesian version is effectively you have to allow all the weights in the model to be random variables, And somehow you need to compute the posterior of these random variables. The posterior is very high dimensional, so you're going to need to do some approximations. And what we're actually using is, we use earlier work from my colleague at Cornell, Andrew Wilson, that goes with the name SWAG. This is stochastic weighted averaging, and I think G stands for Gaussian. So literally what you have is you approximate the posterior of the weights as a Gaussian, but you approximate them with samples. So this is not like a Laplace type of approximation. It's a little bit better based on samples. But if the weights are coming with a posterior distribution, you can predict this time series, but also with error bars. And so I'm going to take you fast because I want to move to other type of more interesting problems. You can show that these techniques work quite well. So this is the 1D paradigm, the KS equation, mimicking turbulence, but not rate. And the spectral energy density comes to approximate quite well with solutions known from direct simulations. And I don't know if there was any animation anywhere. So it works, okay? And a limitation that this method, like many of these methods have, is because we use these recurrent connections. If you provide me, if I try to train the model by computing, let's say, the potential over time steps that they're a significant distance in between themselves, then you will have the same problem you have with other methods that require dense information in time to compute gradients. So, obviously you want to avoid vanishing gradient situations. So literally the system, the way it is trained is trained over a very small time period and then gets updated if the predictions that you do later on, they are not satisfying the loss function that I indicated a few slides ago. So you can actually start modeling problems also with discontinuities, and you can see here results with the 1D Viscus-Berger equation. You can do very well with predicting the SOCs, and actually even you can show that the uncertainty in the SOC locations is the highest, so you can have error bars. And again, for a given input, you produce a posterior of the responses and you can actually sample. So this is the exact solution for the test case, and the rest that you see are realizations from their posterior samples. Okay, for each sample of the weights, you have a mean prediction. So when you put all of this together, you get these realizations that you see here. You can apply this to 2D and 3D problems, and this is the 2D Viscus-Berger equation. And again, the error bars are the highest where the SOCs take place. And the methods, of course, once you train the system, is way faster than solving with, finite elements or finite control volumes, the same problem. And of course, all of the simulations are in the context of surrogate modeling. Okay, let me, before I move to more new type of, works, let me just try to expand on these surrogate dynamical problems using no data, and discuss a little bit the use of these mappings from X to Y that I referred to before with invertible neural networks. But let me make it a little bit different here. So what I'm going to do is I'm going to assume that I have a model that I can solve it at different scales. So I can solve it maybe at some coarse scale, and so the X that you see here is a coarse scale solution. And then somehow I want, using the coarse scale solution and the potential of my governing equations at the fine scale, I want to produce what the fine scale solution Y will be. So I want to produce Y condition on the coarse scale solution. So you can think that it's maybe easier and cheaper to generate a coarse scale solution, and certainly cheaper to generate data on coarse scale. So can we actually produce a fine scale solution, Y condition on X? So again, X here is not the input, is a coarse scale solution corresponding to some input. I use X to keep the notation for the network similar to what we showed before. So literally the network looks similar to what you showed before, but the only difference is now that X is this coarse scale solution, all right? And Y is the fine scale solution that we want to predict. And what you do is, you extract coarse scale features from X similarly to what I did before. Those have to condition the responses Y's at different scales. And because the problem is dynamic, you have to extract recurrent features that I indicate here with H and C, that you have to feed them to LSTM blocks. And then there are latent variables Z that you have to sample both for training and being able to do predictions. And all of the Z's that you see here are nothing else but Gaussian, Gaussian distributions. So there is a lot of fine details that go on this that you have to read the paper, but more or less the structure follows the multi-scale nature that I indicated before, and the whole nature of the formulation is convolutional by design and invertible. So let me stop on this slide and mention particular issues that came up with this problem. So remember that the idea here is we have the solution at some coarse scale, coarse scale, and I call that X, and we want to compute a time series Y in fine scale using a potential that is a discretized potential for the fine scale equations. So when you try to use the reverse KL divergence the way that I had it before, immediately you realize that this reverse KL divergence gets stuck in local minima that effectively don't represent the true physics of the problem. And you can try to see this actually even with trivial problems. So the solution to that, it turned out to be the fact that this type of formulation needed regularization through a little bit of data on the fine scale. So what is interesting with now this paradigm is that we do the opposite of what people in deep learning do. So people in deep learning use a lot of data and a little bit of regularization based on some model assumptions. In our case, the whole formulation is based on minimizing a potential that represents the model, and the regularization comes from the data. So exactly the reverse of what you usually see in typical data-driven approaches to these problems. And the data here don't have to be on a fine scale. I mean, they are on the fine scale, but they don't have to be everywhere given. They can be in irregular locations, both in space and time, but you need a certain amount of fine scale data to make this to work. And so we have used this in the context of a model that we call TM-GLOW to model high fidelity turbulence-like solutions. And you can see predictions of, this is the high fidelity solution using a finite control volume approximation. This is the low fidelity solution. And the rest are samples from our Bayesian model that are all conditioned on the low fidelity solution. Okay. And again, the results are given in the reference on the bottom, and there is on GitHub a code that does this type of calculations, and you can see it if it can work in your own type of applications. And again, you get error bars and statistics of the response. So it's not just that you can generate multiple samples, but actually you can generate the Bayesian statistics for the system response as well. Okay, I only put 2 slides because it was on my abstract on inverse modeling. So I am not going to spend more than a few minutes. But let me, let me mention the. I'm trying to put my timer to see where exactly how I'm doing with my time here. So let me mention the classical way for doing inverse modeling, right, is in a Bayesian setting, is to use a surrogate modeling for your direct forward model, because that's the expensive likelihood calculation. So a lot of people, including ourselves over the last 10 plus years, that people are using Gaussian process-based surrogates and AI surrogates and all of these things. But now there is a new paradigm that in addition to do that, you may want to use generative surrogates that somehow learn the mapping from some latent representation of the property you try to estimate in your inversion task to the high dimensional input. So let's say if your objective is to compute some permeability in some groundwater model, given some sparse measurements of, let's say, concentration or pressure or flux, what you can do is, instead of learning directly the permeability, you can actually learn a low dimensional embedding of that. And if you already have a generative model that allows you to go from that low dimensional embedding to the high dimensional K, then effectively you have an easy way to do inversion tasks. So it turns out that there are lots of difficulties with this, and a lot of the generative models, including similar to the ones that I presented before, they have issues with the fact that for a given realization of your latent variables, the K values that they predict don't seem to be very physical, or at least, maybe 10 to 20% of them come to be completely unphysical. So you can think trying to predict a channelized permeability, and many of your samples that you get from your generative model are channels, but they're broken channels. So there is no continuity. So there is lots of interesting, fancy things you can do that I will not have time to discuss today. So there are multiple solutions, including using these invertible neural networks that I discussed before. So that's recent work that came up at JCP a few months ago. You can use adversarial variational autoencoders, because VAEs alone did not work for us. And then you can also use multi-scale VAEs, and that's recent work with collaborators of mine from China that you can download from the article on the bottom. So the idea here is you pre-train a generative model to take you from these Z variables to the high dimensional permeability field, but you do this in hierarchies, building in a smart way generative models that use coarse information to proceed to fine information. So the only message I wanted to, by throwing this example, is now we have a surrogate model that can be based on deep learning, but also we can have generative models that actually facilitate the inversion process by doing inversion to a low dimensional embedding, and then use the generative modeling to go from there to the high dimensional property. Okay, so let me, I inserted a lot of slides last night on something more recent on doing dynamics using transformers. For those who have not seen anything about transformers. So transformers is basically a network architecture that is the state of the art in natural language processing, in things like doing translation, for example, text recognition, sentence to sentence type of calculations. And you see an architecture of transformer on this picture. So these transformers are based on what's called self-attention. And why this overtook natural language processing the last 2 years, they overtook it versus sort of standard techniques because they don't require any recurrent connections. So all of these issues with vanishing gradients they disappear here because you don't have anything like that appearing in training or in testing. And I will show you how is that being done. So the question when we came up with this across these transformer models was, can you actually use transformers to model physical dynamics? And so we started playing around with this about a year and a half ago. And so the work, I'm going to give you a reference for those interested. So let me explain what the idea of transformers is and then how we use this for dynamical systems. If you have a time series, and I'm referring here to language modeling, to a series of words in a sentence. If you try to use recurrent neural networks, then you have to learn this, future states here that you pass them from one LSTM block to the next, right? So using recurrent connections. And so somehow they try to capture the context of the different words, okay, in an implicit fashion. And then another model that has been around is to try to figure out words of similar context using convolutions. So if you try to do prediction, let's say at time 2, what you will do is you will use a convolution with some kernel that looks in the neighborhood, it looks the words around, and it's trying to find the similarities, let's say, of the word let's with represent and represent with this, okay? So obviously all of this require extensive calculations to make them to work. And the most difficult, of course, thing is that you have this vanishing gradient issue because of the recurrent connections. So you're not allowed really to do long-term time integration or prediction with this type of models. So how does attention works? It's very simple. Again, I'm using this language paradigm here. If you try to do, let's say, a prediction at time 2 for the second word, so what you will do is, obviously you will use some embedding of these words, and I will come to it shortly, but you will try to compare the embedding, let's say, of this word represent with the embedding of the word let's. Okay, so you do some sort of comparison, and from that comparison, you extract, if you like, a measure of the similarity of the word let's and the word represent. And then somehow, when you're ready to do prediction at time 2, you will take a weighted average of all the embeddings of these words, multiply with these weights that came out from this comparison that you did between the embeddings of the second word with all the other words. So that's what self-attention is, and that's exactly what we're going to try to do with physical dynamical systems. A little bit of algebra to show that there is not going to be any recurrent connections on this. You're going to have to build local neural networks for a given input xi to compute what's called the values. These are the value vectors. This is the query vector, and this is the key vector. And before I had this comparison of, at a given time, of the query vector with the key vectors of all the other words. So that's what is called here a score. And you can think of this being really an inner product type of calculation. And then what this is, it's basically a way to do normalization using a softmax calculation. So we normalize all the scores so they sum to 1. And then once you have the scores, you can take the values of all the words that you have, sum them up weighted by this coefficient alpha, and that's your output at time n. So you look at all the words everywhere at all times, and you try to figure out how relevant they are in making predictions at a given time. And by the way, you can appreciate that all of the calculations that you see here, they can actually be done in parallel, because what you can do is if you define this K, Q, and V values as vectors, you can actually, I think I have an equation somewhere, but you can show that you can do all of this in one step. So there is no recurrent connections or anything like that. So if you want to do prediction at time 3, this is your query vector at time 3. and you will have to compute inner products between the keys at all other times with Q3 and compute these attention scores. So how much in context every word is relevant to the prediction you try to make. And then at the end of the day, take these attention scores, multiply them with the values of each word and do predictions. So we're going to try to do the same thing for physical dynamics and see if that thing is going to take us anywhere. Okay, so I mentioned before, the whole thing can be parallelized. So you can write all of these calculations of these scores in one step, okay? And to make it interesting, in the original work of on transformers, rather than doing this as one-step calculation, you use what is called a multi-head attention. So you split the calculations in multiple heads. So think of this, what I described before, think of doing it multiple times, and then all of them in parallel, and then averaging, sort of like a Bayesian model averaging, if you like. Okay, so this is going to be this is what's called a multi-head attention model. Now, for the particular results I'm going to show you, we use what is called a mask self-attention because we want to mimic time integration. And when you do time integration, to predict something now, you only look at what's going on now and what happened before. You don't look in the future, okay? So for example, to do predictions at time 1, the previous diagram, it will look like this. To do predictions at time 2, you only have to look at the information at time 1 and time 2, and similarly for the remaining of the time. So this is what is called a mask attention. Now you may say, if I look in the future, that is very well known to add stabilization to the problem. Actually, my early career solving inverse problems was using future information to do predictions at the current time. So you can actually think of doing that as well. We haven't tried, but right now we try to mimic time integration that allows us to look all the way to the past, not just at a few time steps, but all the way as it is needed by this attention scores that the model is computing. All right, so the model is similar to what I described before. There is an encoding, there is a decoding. The encoding requires an embedding of the input. So we will have to discuss what that embedding is going to be. So the encoding involves the multi-head attention that pays attention to both the past and the future, but the decoder looks only at the past, so it uses a masked multi-head attention. But more or less, in addition to this attention models, there is a little bit of feed-forward type of connections, and the rest of the model is basically rather simple. There is not much complexity on doing this. I forgot to mention that these models require a positional embedding of the words, and in a dynamical system, that's very natural because it introduces a time awareness. So when you provide a state, as an input, the system, the network immediately knows the time that that input refers to. So there is a time awareness in this type of models. So we use what is called the open GPT for the results that I'm going to show you. This is GPT, I suppose, stands for Generative Pre-Training Transformer. And the word pre-training here is extremely important, right? It implies that I'm going to pre-train the model. So when I have a new dynamical system, I can start doing predictions without any further need for training. So if you download this GPT models from Open AI, it's already pre-trained and you can start doing natural language processing tasks without any training from your side. So eventually, hopefully, we would like to do the same type of calculations. All right, so let me, I'm taking my time here. So let me say, so what is the encoding for a true dynamical system, a physical dynamical system is going to be? And the answer is we decided to actually use a Koopman embedding to do this, okay? And I want to be sure that when I talk about coupon embedding here, we want to infuse some physics to the embedding of the model, but literally, I have no interest to use Koopman representations to actually solve the problem and compute Koopman dynamics. I only want to produce, using Koopman, to impose some physical context to the problem. I want to introduce some sort of a physical bias, if you like, in the embedding. So once I compute the embedding of a given state of the system. So let's say phi is some velocity field. Once I produce this embedding xi, I don't really need anything but the decoder of the system that will allow me to go from the xi state to the actual physical, let's say, velocity state. So I'm not going to use the Koopman metrics or anything like that, right? We only use it to impose, again, some physical bias to the model. So how is this going to work? If you give me, let's say, the velocity field, I am going to produce an embedding C1. I'm going to feed this to my pre-trained transformer so that you provide C1 and the transformer starts doing predictions in time. And once you want from a given Xn to produce Phi, you will use your decoder and produce that state. So that's all there is. Does it work? Well, all the problems we worked on, and again, that's a limited number of problems, it works quite well. It actually gives better results than other type of embeddings. So actually, we realized that even trivial embeddings work quite well, even though they don't capture the complete physics, especially when there is transition in dynamics. And I'm going to mention this flow, the flow past the cylinder case. But the Koopman embedding had the minimal error, and overall, basically, we gave the most satisfying answers from all the other methods that we tried. I wanted to, I don't have time to elaborate on the picture on the left, but a typical question that comes about is, if the transformer learns a time integration, what does it really learn? Does it learn any particular time integration? So the only thing I'm going to say, because we use this, multi-heads to do time integration. So we use, as you can see here, there is multiple heads and there are multiple layers in the transformer network. And for each of them, we produce these attention scores. So effectively, the transformer treats the multi-scale dynamics problem as a truly multi-scale integration problem. It does a different integration at every head, at every layer, and then it averages all of these results to produce what it produces. So it doesn't fit in to this particular integration scheme or another, but the bottom line is it pays attention to whatever it needs to do an accurate integration. You don't tell it what to do. And again, these are results, more details for this flow past a cylinder. And as I mentioned, other embeddings seem to work. The Koopman embedding is the only one that actually captures the transition from laminar to periodic vortex setting. All the other models, basically, all the other embeddings cannot capture that property. But I need to put a disclaimer here for the people in natural language processing so that we are all prepared for what the future may be. In natural language processing, everybody started with very complex embeddings. And then the current state of the art is that simpler embeddings actually are the ones that work the best. So we don't really know yet what the future will hold on this, but the idea is the transformer can take whatever embedding of your dynamical state you can come up with, including even principal component analysis, if that's what you would like to do. Okay, I know my time is over, so if I can have, it's 12:51, so I'm going to take a few minutes to tell you a little bit about what is coming up, right? So you notice that much of the early conversation on the presentation was that to drive this limited data or no data simulations, you need to know the force field. So the idea of the force field driving actually both these predictions and surrogate modeling, it was, to us at least, it came from the work we were doing with molecular simulations. So it turns out that if you actually look carefully on simple models of molecular dynamics, including Brownian motion, you can actually show that the force field, which is the gradient of the potential, is actually directly related with the Koopman generator. So effectively, learning the Koopman generator, it is effectively the same as learning the force field. So we are concentrating the last 6 months or so in learning the force fields in certainly molecular simulations, and you see some results on this slide from a recent work of my postdoc, Chris Obal. But generally speaking, everything that I presented before, if you don't know the Lagrangian, and you say to yourself, can I actually learn it if I have limited data? The only way you can do that is by learning the Lagrangian on unstructured grids, and that required graph representations. So all of these things that I was referring before, to make them to work, and at the same time work for a Lagrangian that you learn from limited sparse data, you really have to use graph neural networks and graph convolutions to do this type of models. And that's an area that is exploding, because now we have PyTorch geometric that allows you to automate in many ways a lot of these calculations. And of course, if you learn the force field, you don't need any differential equations. The force field is all you need, right? And so if you have the force field, you can actually do zero data molecular dynamic simulations. And I have shown these results. I don't know if the movie will play. I have shown these results before, where effectively you sample in a two-dimensional latent space, you move across actually 4 different material conformations, and you generate realizations of how the molecules look like. And the only thing here, again, is the knowledge of the force field and evaluating the force field at sample locations of the material state, not the exact ones. So really, we envision one day where we will be able to learn this force field and at the same time use the learned force field to do Bayesian predictions using this transformer type of models. So let me finish. The first thing I wanted to conclude, right, is not just that the no data paradigm works, because it does work, but I think being able to minimize the amount of data needed to do physical simulations is here to stay. But some interplay between data and models is needed, because I'll show you the turbulence case where the model alone is not sufficient to actually get you the right solution. So you need data and models. The second thing is attention. To me, it's something that is going to stay. And if you are interested for philosophical statements, you can see a recent reference by Jeffrey Hinton that basically characterizes the self-attention models as the models to stay for the next generation of machine learning. And the key ingredient there is to do pre-training of transformers. So imagine some of us, pre-train transformers for different applications in fluids or dynamical systems, and then we pass them to the community, and they can start doing predictions in related problems, but without any further need to train. This is now the state of the art in natural language processing, and maybe we can do the same thing in physical dynamics. Learning of force fields is a huge area, and there is much more activity actually in molecular simulations these days than anywhere else. But as I discussed, this is a universal theme that penetrates the differential equation world as well. So learning the force fields is important. Did not talk at all today about enforcing, especially in the graphical neural networks, equivariance, so symmetries. That's an important topic. But certainly, if you're interested to do works in unstructured grids and topological spaces, you really have no options but to move to graph neural networks. And there is much excitement there, not only to do Koopman embedding on the graphs, but do transformer modeling of graphs and generative modeling. There is much work to be done in that area, and I think that's a fruitful area for collaborations and future work. Let me just stop there so I can leave, unfortunately, 3 minutes, but I'm sure we can move a little bit past 1 o'clock for questions. Thank you.
All right, thank you very much for this great talk. So we have time for questions. We can stay a bit longer after 10 if needed. So if you have any questions, just you can ask in the chat or just raise your hand. We can you can ask it live.
Do I have to get out of share to see the chat box?
Or you can, yeah, you can read the questions from the chat box. Well, I'm still looking. I don't know where. Let me see. There are still no questions.
No questions. Okay, all right. Maybe that's why.
Yeah, let's see anyone.
So maybe I can start with a question, Nick. So, this is a fantastic idea, thinking about sort of having these pre-trained physics modules. Do you think you could almost think about a physical system and say, look, I've got some diffusion in here. I have this kind of nonlinearity. Can I pull together different physics pieces for these pre-trained modules? And obviously linear superposition doesn't hold, but these are nonlinear devices, right? I'm wondering if you can kind of glue together and say, I know I have this physics. I'm going to take these pre-trained modules, put it together. I'm sure you must have thought about this.
Yeah. If you want to see in action how these ideas may work, look at things that people are trying in this field of meta learning, where effectively, you train the model with a lot of data on, let's say, diffusion and advection and this and that. And then once you train, you have an outside optimization loop that allows you to move to a new task with actually a minimal amount of information. So these ideas in meta learning have been very successful, but for simple problems. And I believe there is room to actually do similar type of things, but they're not sort of automatic that I can tell you, here they are ready to go. But certainly this is something to strive for, because the community will never accept something that requires 1 billion of dynamical system simulations, to train before they do a single prediction. So there is, I think, a potential there under the context of meta learning, that I have only seen it applied for regression models in very low dimensional problems as of now. So I have not seen it actually applied to dynamical systems yet, but I want to be optimistic that this is, if it works in NLP, it should work for our world as well.
All right, so we have another question in the chat, 2 questions. So Keith asks, can you summarize the status of neural networks at learning structure of PDEs? For example, learning the invariants of an integrable system such as KDV or NLS.
So the only good work that I know in modeling invariances and symmetries and equivariance in general is in the context of molecular simulations. To the best of my knowledge, nobody has yet applied this seriously to extracting this from data that come from PDEs. So that is a completely unexplored world, but things are changing rapidly, and so rapidly actually that there is a Google team, and you can search because they have already 2 publications on archives that use these graph representations and these methods to learn equivariance for unstructured data on graphs. They try now to extrapolate and using the same ideas for data that come from the solution of PDEs. But it's a new area. People have not yet populated that domain.
Okay, thanks. So another question. Does the transformer predict the next encoding or the delta to add to the current encoding to get to the next encoding?
Yeah, so the transformer only predicts the encodings of the output, and you need to have a decoder that tells you what the physical state will be, but the transformer predicts the whole time series. Not just one time step at a time, predicts the whole time series. So for a dynamical system, you can think you provide an embedding, let's say, of your initial state, and then the transformer will start doing predictions, and it will give you the whole solution for as long as you want to, paying always attention at all the previous time steps, doing this complicated multi-scale integration that I referred to before.
Okay. Maybe one last question. So far, embeddings are specific to a given scale. Would it make sense to have embeddings capture interscale constraints analogous to how NLP folks have sent or dock level embeddings?
It sounds, you remember when I was showing this multi-scale architectures, right? The whole idea was to extract embeddings of, let's say, the input at different scale and then condition the outputs at these embeddings of the input. So sort of solving hierarchical multi-scale problems at each scale. So I think that's an excellent idea. And in principle, the transformer network, because it's hierarchical in nature and has all these layers, in principle should allow you to do that. We haven't really thought about it doing that yet, okay? But if you have different layers in your transformer, maybe you can think of feeding different embeddings of your input to the different layers. So that way you build sort of a hierarchical multi-scale transformer. And remember, the transformer, as complicated as it looks, is actually has this attention and these fully connected networks. So there is much room to adjust the architecture in the context of physical dynamics. We just, as of today, we haven't bothered to actually put our hands on that. We wanted to see if, sort of do a feasibility study and see if it works. And so lots of these questions are on the air for people to actually research on.
Okay, great. So maybe if you have time for one more question, let's do that. So there's a question by Dima Burov. Does transformer induce a semi-group? That is, prediction at t equals t1 plus t2 is the same as changing the two predictions for t1 and then t2?
I can only guess. The answer is no, okay, but we haven't investigated. So remember that in the transformer, you provide a time embedding. So you not only you give your state, you give actually the actual time. So if I try to actually build some sort of group theoretic arguments here, the time awareness may blow up and destroy the type of that type of reasoning. So I am going to guess no, but we haven't really investigated that yet. When I tried to communicate actually this recently to a federal agency about the time awareness, I told them the only thing I know about capturing time awareness is really the transformer. And they asked me, what is the transformer? So I gave up at that instant, okay, because there is too much to investigate, but people still are not familiar with what a transformer is.
Yeah, that's exciting. Lots of exciting, things to try in that world of transformers. I'm also not aware of a lot of research going on there for physical systems, but do you think it would these models will generalize for physical systems, given don't they face the same problems of your neural networks in physics in general, where there's generally overfitting, and you tend to interpolate more than you actually extrapolate, and on things that you don't know physically.
Yeah, I do not anticipate, and I have not seen any of those problems in the context of natural language processing. And I think, I don't know if the original paper on transformers, and attention, going with the name attention is all you need. But as Jeffrey Hinton summarizes in his paper this year, indeed, that attention may be the only thing we need in the context of these dynamical models.
Yeah.
I mean, to me, this is a sort of one of the most exciting ways to look at, generalizing with neural networks time integration, because effectively you don't prejudge on what previous states you need, or what's the order of your integration scheme that you need to do accurate predictions, because your model looks at all your previous time steps and computes how relevant they are to your predictions that you do. And they do this, at multiple layers, in a sense, capturing the multi-scale and time nature of the problem, but in hierarchies, in a way that is very complicated. And if you look at these scores that these attention models learn, they are very difficult to interpret in the context of numerical time integration. So I will try to even not to use the word anymore, time integration, because that implies certain things that the transformers don't necessarily try to mimic.
Okay. Yeah. All right, that's great. Thank you very much for this talk, and for all these great ideas to explore. We're glad to have you for this seminar, and in 2 weeks we will have our last talk in this series for this academic year, and we're looking forward to having a more conversation about these topics with you again. And so have a great weekend, and thank you all for being here, and see you next time.
Thank you for the invitation. Thank you for listening. Bye.
Thank you. Bye.
Thanks.
Bye.